All right, hi y'all. Today we're going to be going over, let's see here, we're going over exam 1 in the fall of 2022. And this is just your classic pointing vector problem. Now, this isn't your exact classic one, but it is a pointing vector complex power problem. And you'll see this every single time for your first question, especially for the exam coming up on Tuesday. Now, let's start here by trying to understand some, maybe not understand, but getting some equations down that we will definitely be using for these problems. The first one is, it says find the complex power, denoted by P subscript C, is equal to the surface integral of the pointing vector dotted with its normal vector with respect to the surface area. But we introduce a new variable, S, your vector S, your pointing vector. S is equal to 1/2 multiplied by the E vector, your electric field vector, cross product with the conjugate of the magnetic field vector. So these two equations you'll be using a lot, especially in this first one. You'll always use these these equations. Now let's get on to this problem here. It says a lossy coaxial cable, so lossy, we're losing some energy here. We're losing some power along the way. The coax is filled with the lossy dielectric. Okay, well, we're losing more power. Okay, the fields inside the coax are given in cylindrical coordinates. Of course, we have a coax by this, phi hat and rho hat, okay, so we're getting this, where the complex intrinsic impedance of the dielectric material is given in polar form. Remember, polar form, it gives you the magnitude and your phase. You can use Euler's identity to change it into cosine plus j sine of your phi value. In our case, that's rectangular, where you're given it in polar. That's very important for this type of problem. And it says find the complex power. Perfect, we found the complex power here. It is flowing in the z direction. That's very important. The positive z direction at any point z on the coax. Okay, well, let's see, positive z direction. This means this normal vector here that I'm circling will be, this will become z hat. That means right away we know this complex pointing vector must be a z hat. If it is not a z hat, we take the cross product between two different normal vectors. It's going to be 0 because they don't have anything in common. The dot product, mind you. If they're the same, then all of them go together. If one is negative, you just take the negative of it. That's just some Cal 3 stuff, right? We have to remember this dot product and cross product stuff. Okay, so now what we need to do first is we need to calculate the complex pointing vector. Okay, so complex pointing vector, we take E, which we can rewrite E equals, we really don't actually, we just say E cross H conjugate. Let's figure out what the conjugate of H is, though, because that is important. We already know what E is. E doesn't change. H conjugate. The conjugate means anytime you have a J, flip the sign. That's all this means. So what we're going to do is we're going to, let's see, we have a phi hat. Keep that the same. 1 over the intrinsic impedance. Now we need the polar form of this. So we need an E. Okay, we have a J. That's our first J. Is it positive? Yes. So we change it to a negative because we're going into the conjugate. Now we have 1 over rho. That does not have any J in it. We keep it the same. E to the negative J beta Z. Well, that negative J becomes a positive J. Finally, you have an E to the negative alpha Z. That doesn't have a J, so you keep it as the exact same. And now what we need to do is we need to take the cross product of them. So the cross product, this is something I recommend you put into your formula sheet that you can make, especially the cylindrical ones, and of course your spherical ones. You never know what you're going to get. Put all of them on here just in case. They could get very tricky with these types of problems. Now, what is the cylindrical coordinate cross product? Cross product in the cylindrical coordinates is 1 over rho hat. Okay, let's start with E vector. Does the E vector have a row component? Yes, it does. It is 1 over rho e to the negative j beta z e to the negative alpha z. Does the H component have a row vector? No, it's 0. Now we have rho times phi hat. Does the E vector? E vector only has a row component, so we can just fill in 0 for everywhere else. And the H vector, it does. We have it right here. Well, let's rewrite this. We have 1 over the magnitude of n, e to the negative j phi, 1 over rho, e to the j beta z, e to the negative alpha z. Did we forget anything? Well, in fact, we did. We need to make sure and multiply this component specifically by rho. Why is that? Well, that's just the equation given in the notes, right? We have to do rho, I believe they do, rho times a of phi, right? I think it's like notes 3 in complex vectors, something like that. Now you have your z component. These are both zeros. There's no z component given. Okay, so now we do your regular cross product. Y'all should know how to do this at this point. 1 over rho, you do rho hat. That's going to be 0 times 0 minus 0 times that big number, 0. Now you do minus rho phi hat. Okay, rho phi hat, we cover the middle row. We have that big number times 0, 0 minus 0 times 0, 0. Then we do plus the z component. Now what we have is these two numbers being multiplied together. Okay, that's good. What else do we notice? Well, we notice that this row cancels with this row. Okay, that's cool. And we also notice, we can rewrite this here. We have 1 over rho, magnitude of intrinsic impedance, e to the negative j phi. Wow, that is terrible. Then we have e to the negative j beta z times e to the j beta z, or plus j beta z. Well, this becomes 0, and that becomes e to the 0 is equal to 1. Perfect. And then we have e to the negative alpha z plus negative alpha z. When you multiply, you have to add the exponents, and this becomes e to the negative 2 alpha z. Awesome. And then, of course, it's minus 0 because of this here, right? 0 times 0. All right, so that is going to be our E cross H, our cross product. But we know the complex Poynting vector is equal to 1 over 2 times that. So then we have 1 over 2. We can call this 1 over 2. We can keep it like that. And then we have the z component. 1 over rho times 1 over rho is 1 over rho squared. Magnitude e to the negative j phi times e to the negative 2 alpha z. Okay, that looks about right. Let me check my answer before I tell y'all that's right, but I believe that is 1 over 2, 1 over rho squared, e to the negative j phi in the bottom, 1 and okay. So it looks like they put e to the j phi on the top. That works too. You can move the j, and we'll do that for reasons coming up certain very soon. So we'll put e to the j phi here. Okay. If you don't know how I did that, it's 1 over e to the negative j phi is equal to 1 over e to the j phi. And this becomes, you can multiply both top and bottom by e to the j phi. And this cancels, and then you get e to the j phi. Just know how exponents work. If you put a negative exponent, it flips the sign, or flips, go to the numerator, denominator, however it works. So this is our complex Poynting vector, or our Poynting vector here. Very simple. This should be standard practice for everyone now. Now what we need to do is we need to find the complex power. Complex power, given or denoted by PC, is equal to the surface integral of the Poynting vector dotted with, in our case, in the positive z direction with respect to s. S is not the complex Poynting vector. That is surface area, I guess. So now what do we do? Well, we know it's a cable. What shape is that cable? Well, it's cylindrical coordinates. A lot of the times in problems, they'll give you these bounds for your integrals. They'll say this, 0, hello, okay, oh, wow, 0 less than phi less than 2 pi, and a less than rho less than b. These are your integral bounds. Now, which one comes first? Well, typically you will integrate over the circle area first, or the radians. This is because when you look at this here, we're going to take the integral at this location. We're going to take the integral at the base of the cylinder. So what you're going to do is you're going to integrate over, if you have this radian here, you're going to integrate over this entire circle, and then you're also going to integrate over a and b. Well, why a and b? Well, in our case, it's because we have this, dielectric here, and then we also have the outer part of your coax cable here. You have sort of like a cylinder inside of a cylinder, right? So you need to integrate over a and b. So from there, and actually a lot of the times it will say at z is equal to something like at z is equal to L, or z is equal to z naught, something like that. What you would do is you would plug in, for every z you get in your equation, you plug in that value. Whether it be L, whether it be z naught, whether it be negative L, you need to be careful about where those values are coming from. Now what we need to do, this surface integral, just like I had said above, breaks up into a double integral from 0 to 2 pi on the outside, a to b on the inside. And now what we need to do is we need to put in our complex Poynting vector. I'll copy this here. Okay, we'll copy that here, and then we need to dot product with the z component and take the integral of rho d phi. Do not forget about this rho d rho. This is your Jacobian. You cannot forget about this. If you forget about it, you're wrong, totally wrong, and you'll notice it because you have to take the integral of 1 over rho squared, which is, I don't know, like negative 1 over 3, something like that. But yeah, you have to take this nasty integral. It should just be always natural log. So that's a way to check. Now what you need to do is, you notice the dot product of this is the same thing, just get rid of the, your normal vectors. And now you have to take the outer integral first. So, well, what do we notice? We have the integral, hello, oh my god, that's terrible. That's whatever. The integral from 0 to 2 pi, and I'm going to disregard all of the rest of it. I'm only going to do the integral from 0 to 2 pi of e to the j phi, d phi. Since we're doing the outer integral, and this is the only portion of the Poynting vector that has the phi component. Well, what is this? Well, this is equal to 1 over j e to the j phi evaluated from 0 to 2 pi. Well, this is equal to negative j e to the j 2 pi, and actually we'll just leave this, minus e to the j 0. Do we know what e to the j 2 pi is? Not really. If you know what it is, perfect. That's good for you, but I definitely don't. Well, you have to use Euler's identity. So this is what, cosine of 2 pi minus cosine, or is it plus something like that? Plus j cosine, what the fuck? Plus j sine, sorry. Plus j sine of 2 pi minus, put another one here, cosine of 0 plus j sine of 0. Well, what do we know about this? Oh my god, this looks like, that's 1, that's 1, that's 0, and that's 0. So we have negative j times 1 minus 1. Oh, that's 0. Well, don't we take the double integral? So we should multiply this to, well, I mean, it's 0, right? We should just cancel it. No, you have to be very careful because the meaning of this is, the meaning of getting 0 here is not the fact that it just cancels. The meaning of this is, this means that e to the j phi does not affect the power, or the, I guess, time average power it doesn't affect it. Why is that? Well, what is e to the j phi? What do we know from signals and systems? What do we know from just circuits basics? Well, whenever we do phasor analysis and e to the j phi, if we go into the complex plane, e to the j phi is your unit circle, sort of, in complex plane. You have your real part, you have your imaginary part. What does this transfer to in a sort of time? Your time variables here. So now you have time, and this is, I don't know, some voltage. What this looks like is, just a sine wave. What do we know about sine waves? Well, we know the average power is going to be 0 because, positive here, negative here, they cancel your average parts. That's why we have to take RMS. We're not taking RMS here, we're taking averages. So all this is saying, whenever you take the integral of e to the j phi, is that it does not affect our complex power answers. Something else you can think about. Whenever I will quote unquote say regular problems, in regular problems, you don't usually have a j phi sign, or an e to the j phi. You don't usually have that. You usually just take the integral from 0 to 2 pi of 1 d rho. This becomes 2 pi. But what does that mean? Well, what this means is you're taking the integral over 1. You're not taking it over, a signed component. You're taking it over this. You have your x and y components. You're taking it over 1. This is 1. And this would be, what, 2 pi, 0 to 2 pi. So you're taking the integral, the area under the curve, of this entire thing, and it is not time varying. So you have to be very careful with how these words, or how, I totally messed up on this problem. I thought it was 0. I was like, wait, how did he get this? I did a little digging on here, and this is why. And to be honest, and I'm going to be honest, this is kind of weird. He didn't go over this at all, but I guess we didn't ask him, so fair game, whatever. But this is all this means. E to the j phi does not affect the time average power, which doesn't affect the complex power. So what should we do? Well, we should do the same thing. You don't worry about that e to the j phi. What you do is you take the integral of 1. Yes, I know. Don't ask me. It makes no goddamn sense. If someone knows how to do it, please DM me or something. But that's what I had gotten from some digging on some research stuff here. So what we do is we take the integral from 0 to 2 pi of 1 d rho is equal to 2 pi, and that's going to be our outer integral. So now what we have is, from above, we have 2 pi over 2. We let e to the j phi be here over the intrinsic impedance, magnitude of it, e to the negative 2 alpha z, integral from a to b of 1 over rho squared rho d rho. Okay. Now, this is your basic one. You take rho, you get natural log of b over a. So what we know is the complex power is equal to, this can cancel. We have pi e to the j phi e to the negative 2 alpha z over the magnitude of the intrinsic impedance times natural log of b over a. So that should be your answer for a complex power. Okay, what else does it ask? Is that it? Complex power? Yeah, that's it. I'm going to be honest, I see what else he did. I see he changed e to the j phi to Euler's identity, but I mean, it doesn't ask for that. So how would we know to solve for that? If y'all know what I mean? Yeah, he would have to explicitly ask for that. If you put this, you would probably get full points. All he did was change real of PC is equal to e to the j phi is cosine of phi, so pi, you can put cosine of phi up here, doesn't matter, e to the negative 2 alpha z over the intrinsic impedance magnitude, natural log of b over a, and this is in watts. And then you put j, e to the j phi is cosine phi plus j sine phi. So your imaginary of the complex power is equal to pi sine of phi e to the negative 2 alpha z over the intrinsic impedance in natural log of b over a. And this is in vars. VAR. Okay. So this would be your final answer here. I'm pretty sure he'd be totally fine with this. He won't take off any points. Just make sure you put VA here because this is in volt amps. Now, let's try and make sense of this because this is the answer, but what does it mean? It will help understanding these kinds of things later on, especially since we're going into Smith diagrams and lossy stuff. This is a lossy cable, and we know with lossy stuff, there's going to be power losses. Okay. Lossy dielectric, well, that's definitely going to lose in complex power there. There's going to definitely be, not complex power, but real power is going to be lost. So we know from your, I forgot what it was called, what class of engineering mathematics, where we went over ordinary differential equations, but also whenever in signals and systems, y'all glaze over this, you guys kind of go over this, but there's this thing in the complex power equation, e to the j phi, e to the negative 2 alpha z. This is an dampening oscillatory equation here. What it means is, your e to the j phi, like we had seen before, is, your regular sine equation, your regular sine graph. This multiplied by e to the negative 2 alpha z. What this introduces is a dampening. So what you're going to get is something like, I guess if you had a constant or like something here, you would actually, no, let's just do this. So let's say it starts here, goes the same, and then it starts dampening. I should probably put it where the frequency stays the same. Your frequency won't change, of course. Oh my lord. You know what, forget it. I'm just going to write something here. What's going to happen is it's going to start doing this. It's going to get very, very close to 0. So it's getting closer and closer to 0. It's going to dampen, and this is the same thing that happens with bridges. Your resonance frequency, I remember from ODE and stuff like that, your resonant frequency, you really want this dampening, especially in mechanics. Anyways, that's what's happening in this. This is the lossy part. You're losing a lot of power, so if you want to put this as complex power in time, you are losing this amount of power. Like if we put here and here, we're losing this much power, and then here and here, we're losing this much power. We're losing more and more power as time goes on. That's what's happening. Okay, but yeah, that's how you do this problem. Hopefully this explanation made sense. I hate that he did this. I hope he doesn't do it in the exam on Tuesday, because it really just doesn't make any sense. I mean, I guess it does, but I'd rather not have to have that. But yeah, this is how you do this problem. If you have any questions, please message me. If not, hopefully y'all get this and y'all are working on problems 2 and 3. I'll probably be posting problems, some videos on problems 2 and 3 later on, bounce diagrams, your oscilloscope trace, your snapshots, and then if you have like a fault resistor or if you have 2 different transmission lines, those are definitely all fair game. But yeah, hopefully you'll have a nice day. Thanks for joining.